All right, so only thing missing is this guy. Also, I don't think that the voice is very good quality, or is it?
So let me see.
Can you hear? Can you just listen to me and let me know how is? It's okay quality. I'm not sure if I'm using these mics or something else because this audio input is not. Yeah, I'm using the MacBook Air microphone.
Okay.
That's okay quality wise. I think it is okay.
It's going to include.
But it's not willing to find this. I think it may be because of this connection or something. It just cannot find this.
Can't you connect it directly to your
I
laptop?
no, it's
Just one port?
two ports, but I'm missing my cable extension. There is no other way to put it. Okay, so we're gonna use this mic system.
It's going to be too much environmental noises, so is it okay?
Okay, so we're gonna go.
So if anybody talks, everybody can hear.
Yeah, so it be like this. I know that even when you're talking, then it becomes to be clear. I can try. I can try to put there's another audio input capture.
Can't you add it?
Yes, but it's not finding this anymore. Something happened. Something happened. So am I actually using this one or something else?
So let me speak.
MacBook Air mic. So we're gonna go with a MacBook Air mic. So if you hear me and if it is okay, this is the way we're gonna go. And then we just need to put this PC2, PC1 on.
And also we have to adjust your height.
Yeah.
It's okay. Okay. So do you want me to bring it a bit to the side?
Why these are not displaying? What should I do here? Cable is connected.
Stockholm.
What was that name? That's okay. Let me. Still the same cable.
Nothing.
God damn it! How is so complicated? No! Don't press that for sure. Or you think that we need to do that?
Probably we need to restart it.
Restart it. Okay, no, it was blinking. It was blinking here. No, not coming.
Are you sure? So
Okay, let's restart the whole thing. This guy is blinking all the time, so I think that it's should be coming. There is a good number of different kind of screens here in this lecture room, but none of them are willing to work today. So this is still,
Yeah.
okay,
So
now,
should I go
yeah.
again? Let me at least this way I can
Okay,
see.
start. And it's gonna warming up. The cable is properly connected,
Okay.
and it's a cable
One. Dot
one, cable one, dock one. Ah, okay, so maybe it was a PC one all the time.
Okay.
Okay, try. This was blinking again. So it's dock one.
Yes.
A lot of clicking.
But there's no sign of anything. So it's a
What number is that?
2.
PC2 or dock?
Dot 2. I don't know, it's in Finnish, you should tell me. Is it duck or PC?
This is dock. No. Good news is this, that because it's only 5 of you guys, so what we could do is that you can take a look at my screen here, my computer screen, and this is the way we can go. Because these projectors are not willing to cooperate today. We will make a final adjustment. This is a kind of funny thing because this is clearly recognizes something here because it's blinking all the time, but it's not willing to display any of these screens. If we could just put the one screen on, that would be enough. But none of them are on. None of them are on. It almost feels that there's a loose connection because it's blinking continuously. Okay, let's try this one. Let's try it like this.
Which one did you connect?
This is still this dock one.
Duck 1.
No, dock two. Dock two. I'm sorry. Yep, there it is. Okay, thanks, guys. It seems that every single day, every single week, so we're gonna close 10 to the
another meeting very
10 to the noon. We're gonna close that time. Every single week, we're experiencing different kind of problems with these technical settings. Either YouTube is not willing to cooperate, or then what happened today that overhead or these projectors are not willing to cooperate. Anyway, so finally up and running. Almost forgot. Respect. Hey, we need to discuss a little bit about the practical matters. The first thing to discuss is that I need to send you a little bit more instructions about the upcoming exam, because there's going to be one exam only. And the one exam only is the one that covers all the material that will be introduced you in a period number 1. Period number 3. So the one that started in this month, January. So there will be no other exam covering the material introduced you in period number 4, because that's more like seminar type of the material you're going to get it there. So it's not easy to organize any kind of written exam out of that. And then I think we are not in a hurry. So my plan is to give you at least 3 weeks time to do your written exam. At least 3 weeks time. And this is simply because I know that some of the students participating remotely, they are in like Helsinki and Tampere and other no-good regions. And these other regions, they have a hard time to make reservations to exam spaces. And I heard that they are rapidly sold out, and it's hard to make a reservation if it is a one particular week. So it's going to be 3 weeks time. This is for your information already. And the first week will be the one that ends February. So let me tell you the week number you momentarily. So it's going to get started in a week number 9. So that's a Monday, 23rd of February. And it's going to be, the exam will be on week 10, which is Monday is going to be 2nd of March. And week 11, which will be 9th of March. All right. Then I was crying in my office last week. And the reason that I was crying in my office was that I got an email from one of the students participating in this class saying something about the safe functions of finite element. And this was such a good note that I was like impressed. Like, how come somebody be so much involved with the safe functions? It was a happy moment, so I was crying because of the happiness. And now I'm going to discuss something a bit more about the safe functions, something that I need to correct myself, because last week I said that the safe functions are orthogonal. So they are not mathematically orthogonal, but they do have a special feature that we're going to revisit momentarily. But if you discover something like that, I will be more than happy to come in my office, and I try to find a way that if you can give me hints like that, how can I improve my teaching, I will be more than happy to offer you some extra unofficial credits. I mean, they need to be official credits, of course, but some kind of unofficial, some kind of point that you can get a better grading from this class. I guess that this class, similarly like the class simulation of mechatronic machine, if you just hang around, it's easy to score high. That's okay. That's okay. It is okay. I mean that I have no problems to submit it, the grades to a student affairs office saying that each one of you are getting 5 out of 5. That's fine. If you guys make an attempt the similar way you did an attempt in a simulation of mechatronic machine. All right. So we're gonna get started today by discussing a little more about finite element safe functions. And then we're gonna discuss shortly about the accuracy of finite element method. This is gonna be actually the stuff that I'm not necessarily able to cover today, but I would like to focus on stuff that is related to model reduction technique and how we can make it happen, the model reduction technique, with help of eigenvalue analysis. And what is the eigenvalue? What that stands for? What is that it can offer to you? The way should you interpret the results of the eigenvalue analysis? That's going to be the subject matter of today's lecture. Right, and then before that, just a final adjustment. I need to put myself here in using my phone to the YouTube channel to see if there's any major crisis going on in the streaming. So this is now live in YouTube channel. I want to take a look at the live here. Okay, so I'm not sure if this came this week or was it earlier, that there was a bit of the problem in audio. Was better before the last option changed. Yeah, so the audio today is based on the mic that I have in my computer, so it's not willing to connect these guys. I don't know why. Sometimes it just happens and that's it. Okay, back to the subject matter. A week ago, we learned that there is a method that allows you to combine a finite element model and multi-body system dynamics. And it works in a way that we will make a use of the body reference coordinate system, this one, that is translating and rotating together with the body. Now, what we're going to do is that we simply describe the particle deformation using the finite element model with respect to this body reference coordinate system. And now when doing so, we will collect the strong features of finite element modeling and strong features of multi-body system dynamics. Multi-body system dynamics is very good at to describe large. So we lost the projector connection in a lecture. So why was this? They overheated or what? So they just disappeared. Let me see. There was nothing that I changed. I made no changes whatsoever. You saw me all the time. My hands was visible all the time. So it wasn't me, but now the connection disappeared. So you're still having a problem to hear me. And now we have a problem to display stop by using these overhead projectors. Also, I think that there's something because a display that I'm displaying in my lecture is frozen. So I need to restart this one to okay. Display capture. Okay, so can you guys see this? You cannot. What should I do to put this back on? Annoying like hell. Doc. This connection is, oh, I think there is something, because it comes and goes. I think that there's a loose connection somewhere here. Because if I really press this hard, no. Let me try one more time. Not coming. Not coming. But I see that there is a, because it's asking me if I can connect when I press this hard. Okay, now it was blinking. Dock 1. Remember, so some of you guys have a computer with you. Okay. Because I'm thinking that maybe the one possibility to do this entirely online. Again, this comes and goes continuously here. So it almost feels that there's a really loose connection somewhere. What do you guys say? Should you, so you guys have, each of you guys have a computer with you? Okay. I think because these projectors are just not willing to do anything good for us today. And it's keep on changing the screen all the time because it almost looks like there's a really loose connection. And that's a problem. That's why it behaves the way it behaves. So let me see how this look. The voice quality is not the best possible. Just want to see if this display is okay. No. Display capture. Okay, I'm gonna just take this cable off because it's just blinking and makes hard life difficult continuously. That's it, like this. Are you guys following me? This is kind of ridiculous that you need to follow me online, even that you're sitting here in a lecture room. But see, this is the only way to go today. Just checking that this final change is going to be okay. What do you see in your YouTube? Nothing. What do you see now? Yeah, it comes with a pretty serious delay, so that's why I figured it is correct. God damn it, how annoying stuff. How annoying is this? Nothing comes out like this. If I say Windows, I don't want to use this either. If I use display, it goes like this. Okay, I think it now finally working properly. Yes. But is it so that it's cutting? So it's a little, yeah, it's not perfect setting yet. So one more thing needs to be done. Like this. And now it's going to be perfect. Okay, so protectors not working, mics not perfect. But we don't care, we're still gonna go. I was about to explain this to you guys, that we're gonna make a combination of this finite element modeling by describing the deformation that you see here. So if you take a close look about how things are here, you know, you have where the particle is originally located at, which is described by vector u bar 0 or O, and then there is something that describes the deformation, which is u bar f. This u bar f is the one that is coming out from the finite element modeling. Now, important lesson is this. You know, this u bar f is with respect to this body reference coordinate system. So now when you do it like this, finite element modeling do not need to care about large translations or rotations, which is great because finite element modeling, as it is described here, is unable to describe large rotations. It can describe large translations, but if you look at the kinematics that this is based on, it just cannot describe the large rotations. It can describe the small deformation and small rotation with respect to body reference coordinate system, which is this guy. Nothing further than that. There are specialized finite element codes where the large rotation can be accounted, but on its conventional form, finite element modeling cannot take that into account. There are actually several different ways that you can force finite element models to describe large rotations. And again, the most common source for nonlinearity is a large rotations. All right. You know, limitations that I just say, that the conventional finite element model is not very good to describe rotations, large rotations, that's fine, because those will be accounted by using multi-body system dynamics. That's the way to go. All right, and we learned that the finite element modeling is all based on polynomial expansion. Typically, it is based on polynomial expansion. It could be, you know, in theory, it could be something other than polynomials, but polynomials are basically used because they are mathematically very pleasant. Very pleasant in the sense that polynomials are very easy to differentiate. They are really easy to handle in many different aspects. Maybe their differentiation is the most convenient feature they have, because we do need to differentiate the polynomials with respect to different coordinates, and it's going to be easy to conduct. Now, how it goes in our finite element modeling, then, it goes in a way that we first need to develop the elements that are describing how the piece of structure behaves. A piece of structure behaves in a way that it is connected to surrounding elements by something that are called nodes. These nodes have a certain number of degrees of freedom. In the simplest possible form, the one that is shown here, they can only move left and right. So that means that each of these nodes has a 1 degrees of freedom. This has a 1 degrees of freedom. This has another 1 degrees of freedom. So in total, so it's a 2 degrees of freedom element. Simplest possible element. So what you need to do then is that you need to select the polynomial from your Pascal's triangle such that the unknowns are representing what happens between these nodes. So finite element modeling is all about what happens between the nodes. That's extremely important to understand, because sometimes you hear this explanation that finite element modeling is something that you only focus on the nodal degrees of freedom and rest you have no idea what they are. It actually came other way around. So you first started to describe what happens between these nodes. You are kind of making them to be physical in terms of nodal degrees of freedom. So these nodal degrees of freedom are interpretations to see what happens internally in elements. That's what they are for. So they're telling you that if you introduce a displacement to nodal degrees of freedom, how is that the particles are following that nodal degrees of freedom? But in an element like this, we did not start from the nodal degrees of freedom, but we started from the polynomial expansion. In the polynomial expansion, we need to select 2 unknowns that are selected from the Pascal's triangle like shown here. So you need to select the A0, you need to select A1, that is multiplied by x. If there will be internal node here in the middle, then you need to select another component that could be x power 2, or it could be in the next row, it could be the x power 3 and so on and so forth. But anyway, so then you have more unknowns. And these unknowns will be replaced by nodal degrees of freedom. And nodal degrees of freedom, you can replace them by first expressing polynomials and the multipliers as shown in this part of the slide. Then you take whatever information you have about nodal locations, you take that into account, and then you get relation between the nodal degrees of freedom and polynomial unknowns. Now the next step will be solving polynomial multipliers by inverting this matrix here. Remember the story about my teenage years? Not teenage years, but when I was struggling to invert the element of the matrix, that was a 48 times 48, and that was a miserable time in my life. So that was when I was a postdoc in Chicago. And eventually I was able to do that, but it was all about how to select these polynomials from the Pascal's triangle. And it wasn't straightforward. It was a polynomial where this polynomial coefficient wasn't selected in a row, but they were selected almost randomly. There are some of the good elements in element technology. These polynomials are not selected as in a row. They are not necessarily selected like that, because it can give you elements with a little bit of better convergence rate. And convergence rate was again like how fast your elements reaches the acceptable solution. This is something that is a very critical feature of finite element modeling. All right, anyways, so once we inverting this guy, then we can express polynomial coefficients. And when substituting that information back here, we get something that is called shape functions. Shape functions are relating displacement and nodal degrees of freedom. So if I make a displacement to this node here, it tells me how is each of the particles between these nodal locations, how they're expected to move, which is a little hard to understand when you look at this kind of linear element that can only move in a longitudinal direction. But it becomes to be more understandable when we look at the beam element. So these are the shape functions basically telling that if I'm going to move node here in the left end, each of the particles will kind of move linearly with respect to each other based on these shape functions. And the same holds for the node that is located here in the left. So if I'm going to move it like here, so that all the particles will follow this displacement in a linear manner. All right? But again, If we're gonna take a look at something a bit more complicated, it becomes to be more clear. Something a bit more complicated is a beam element. Beam element that consists of a total of 4 degrees of freedom. It is a 2-node element, so the one node is located here in the left end, another one in the right end, and it has a displacement in transverse direction, and angle here, rotational angle, which is actually described as a slope. Slope in a way that this angle here is going to be described by partial operation, partial v, partial x. That's going to be describing the slope here, angle, if you may. Slope and angle sometimes may be the same story. All right, but anyways, now I have 4 degrees of freedom element, so I need to select my polynomial expansion as shown here. So I have to have 4 components to make them match. How did I select them? I selected them in a way that I select them, each of them based on this. So if I could change the color here, so I selected this one here, which is constant value, this one here, because if not selecting this, element is not capable to move without introducing strain. This one here needed, because otherwise the element cannot introduce the constant strain. The rest you can select the way you want, but I selected like this one, and this one. But instead of these two, I could select something further down in my Pascal's triangle. And what I will get the different kind of shape functions that are describing differently how the element deforms. So the shape functions, in shortly, can be considered what are the ways that the element can deform. And now the special feature of shape functions, the ones that are shown here, is that they will introduce the displacement to 1 nodal degrees of freedom at the time. So if you look at this, the first degrees of freedom is moving left end to y direction. And when you do that, each of the particles will follow this polynomial pattern. This polynomial pattern is significant in a sense that if you compute the slope here, which is my 2nd degrees of freedom, the slope here is equal to 0. As is the displacement here in this right end, that too is 0, and the slope here, when you take a close look about that, that too is 0. So it's introducing the displacement to 1 nodal degrees of freedom at the time. And what I said incorrectly a week ago, I said that the shape functions are orthogonal, meaning that they are mathematically something that they have no relation to each other. That's not the correct statement. That was incorrect statement. So the correct one is saying that each of them introducing the displacement to 1 nodal degrees of freedom at the time, and 1 only. All right, so this is the second one, which is the slope here. You see that displacement here is 0, displacement here is 0, and slope here is 0 too. This is the way it behaves. Now, again, I selected my polynomials in a row, like shown here. What happens if not? So what if I select the polynomials like shown here? So instead of this was a x power 2, this was a x power 3. So what if I am not selecting these ones, but selecting x power 3, x power 5? What's going to happen then? Well, I will get the shapes that are different than they were earlier. So they have a little bit of more curving behavior comparing what I got a little while back. So you can kind of manipulate the way the element can capture the deformation. Now this may be not clear to you, but if I make a comparison, this was based on x power 2 plus x power 3, and this was the one that x power 3, x power 5. You see that this is more, how can I say, it's more like violent deformation. Which one is performing better? It's a little hard to tell, but in element technology, many of the good elements are based on the polynomials that are not selected in a row. It comes, these are non-harmonic, okay, now I don't remember what they are called because it just disappeared from my head. But the risk that you might take when you're selecting this type of the polynomial is that your convergency may not be from one direction only, but it might fluctuate a little bit. Yeah, this is something that I need to explain. Okay, this is again x-axis, which is the number of elements. This is your correct solution. So when you're selecting this kind of polynomials, it's possible that your solution goes like this. Not typical, but in theory it's possible. It's still converging, but not in one direction only. When you have a typical displacement-based element like this, it's always converging from rigid side, like this. Rigid side means that, if you have not enough elements, your solution is deformation-wise lower than accurate value. So it's almost stiffer than actual behavior. So it's always approaching from the stiff side, which in some sense is a safe solution. Well, I don't know, not necessarily, maybe I need to correct myself because safe solution, yeah, because also the displacement and stresses and strains are related. So if you have not enough elements, you're going to get this kind of displacement. It could be in a simple case like, okay, the cantilever beam may be too simplified because you can get this correctly using one element only. But if you get a little less deformation that you should, then you also get a little less strains and stresses that you should, which is can be a risky business because you may assume that the deformation is only this much, when in reality it's in this much. And this can lead to unpleasant consequences. And the strain, of course, and stresses too are underestimated in that sense. All right. Now, my first in-class quiz, which is supposed to be on, is that what is a physical interpretation of safe functions? And the options are, shows the way that an element can deform, defines the rotation of the particles. So we are revisiting what was something that was my favorite in a simulation of mechatronic machine, defines strain displacement relationship, no clear interpretation. Those are the four choices. Let me just double check. I'm a little scared to touch this computer because it's a kind of okay, so I got comments that the voice is not great. I hope that it's still understandable. Okay. Anyways, so again, what I see here that the room number is not correct. So it's a room number is a LUT 26. That's what it's supposed to be. So go ahead and enter your answer. And then just check that. Can you see that the circuit is on? It's on. Okay, should we take a look?
The option doesn't match what
They don't match. What a low performance from my side today. So the way that the element can deform defines connection between the neighboring elements, defines strain displacement relationship, no clear interpretation. So what I see is that the option B was incorrect, different in my slide. But that's going to be anyways incorrect option. Even it doesn't defines the rotation of particles because again the particle rotation is like Santa Claus, and then defines the connection between the neighboring elements. That's a business of notes. All right, so I got 12 answers only. So let's see, the number is counting, so it's coming up. So maybe the case is that some of you are kind of giving up because of the low quality of voice, but this system is not just willing to connect today. All right, I will leave you guys think this, and I'm gonna go back to my PowerPoint presentation. All right, now here comes the main lesson of today. What we can do with finite element modeling is this. So we can put together something that is called equations of motion. Equations of motion that is limiting to small rotations. And it consists of several components. It consists of inertia forces, which is a mass multiplied by acceleration. It consists of something that we have not learned earlier, but it's called elastic forces, which is stiffness multiplied by displacements. And then I have last component that is the right side of the equation, which is external applied forces. So this is the dynamic equation to study structural strength. You know, this is a dynamic equation. In a structural strength analysis, it's very common that inertia component is ignored. And we're only looking for statics. So we're only looking for statics, and in a case like this, so the equation or the equilibrium reads like this. I'm going to just say this F, meaning that these are the external applied forces. So what we do in a finite element modeling is that we are inverting the stiffness matrix, and when do so, then we can solve the displacement. And displacement can be then used to get the strains, and they can be then used to get stresses. And those are the design parameters, design quantities that we are often interested in. So we do care sometimes about the displacement. And often finite element modeling is used to figure out stresses. This is what we like to know more, because they may be limited about material properties. Like in a steel, there's a certain amount of maximum stresses you can impose to it. You should leave a certain level of marginal for that purpose to make sure that your design is acceptable. Okay, back here. This is how your dynamic equation look like. We could make a use of this equation, and we could solve the displacement in a dynamic cases using this by simply taking this acceleration, integrate velocity out of that, and then get the displacement out of that. But that's going to be a lot of work to do, and eventually everything's going to look like this. Big problem is that this kind of the model consists of very high number of degrees of freedom. This is what we discussed earlier. So what I'm going to do today is that I'm going to make myself back here to this equation, and I'm going to reduce the size of this equation by using modal reduction technique, something that Jussi Sopanen is telling you continuously. So what I'm going to do is that I'm going to move myself from the nodal space, where these nodal displacement are unknowns, to something that I call modal space. There is a kind of relation to modal space and shape functions, but what is this relation? This is what I'm going to explain to you next. And I'm going to spend some time to make sure that we fully understand this concept, because once understanding this concept, then that's pretty much all you need to know from this course, theory-wise. Again, we cannot make a use of this one because dimensions are simply too high. There are too many degrees of freedom, so it's not going to be easy to use it as it is shown here. It's actually extremely hard to be used like that. So, these are the questions that we're going to revisit a little later. So what I will do is that I'm going to jump from nodal degrees of freedom to modal degrees of freedom. And these two spaces are related based on assumed deformations. So what are the ways that the entire structure is assumed to deform? Again, so this is the entire structure, how that is assumed to deform. This is the one that relates these two spaces together, nodal and modal spaces. All right, so I do have an accent, so I don't know if you can hear the difference between the nodal and modal. Nodal, modal. Or is it like, woo? Say, doesn't make any difference. Can you hear the nodal? That's note. Modal is a mode. You hear the difference? Okay, because I'm not sure if I hear it myself, because deep in my mind it sounds like, Okay. All right.
Now, like in the previous slide, about there was a power of t to the shape function, but in the second equation it suddenly disappeared. Why is it so?
So the question was, so can you say your question again? Because I don't see this in this one?
Yeah.
Or one back.
One slide back, yeah.
All right. So the question was, all right. I see that this is what they are wondering. This transpose operation of safe functions.
Yeah.
Yeah, this is the correct way to do it is going to be this one. This is a typing mistake here. So they shouldn't be this order. They should be like shown here. You know what this is doing, because there is a possibility that you have a structure like that. It consists of, this is a beam-like structure, consists of 3 nodes. And there may be the case that the force is not that touching to any of these nodes, but it's the middle, geometrically middle of these 2 nodes. Or let's say that it could be 1/3 like here. And you need to express this force in terms of nodal degrees of freedom. How you can make it happen? You can make that happen with help of the safe functions. You multiply your forces with the safe functions, and it's going to divide your forces automatically to your nodal degrees of freedom. That's the purpose of this guy here. Okay, let me change the color one more time. That guy is doing that trick. Where did you find this comment? Where did you find this comment? Because I don't see this in my slides.
No, that was my question.
It was your question.
Yeah.
I thought that it was somewhere here in YouTube. No. Yeah. Another, it becomes to be emotional again. Another happy moment because you're paying that much attention to these slides. Is it okay if I cry?
Yeah.
Just a little bit and then we continue. So we can have a small crying break and then we continue. Beautiful. Beautiful question. All right, and back here. Now why these 2 spaces are important? These modal and nodal spaces, why they're important? That's simply because this allows us to reduce the model, because it's possible that you can easily get much less modal coordinates than your original number of nodal coordinates. How these mechanisms is possible? Well, that's possible because these nodes this one is a nodal vector that includes all the degrees of freedom in your finite element model. It's like I mentioned earlier, it's possible that this vector can easily consist of 100,000 different components. So this ID number could be 100,000 here. It means that the structure can deform in 100,000 different ways, because there are these, each of them are associated to where the structure can deform. Now, is it really necessary that you need to know 100,000 different ways that the structure can deform? Most of the practical cases, no. You don't need to know that many. It's enough if you know some of them, but still describing the entire global behavior of the structure. And when you take that into account, then it may be possible that you can get much less these modal coordinates than original nodal coordinates. All right, so I'm going to use this slide here to explain the deal about what I just said. This is my favorite structure. This is a cantilever beam, which is loaded by freehand, and it consists of 1, 2, 3, 4, 5 elements. And then I have here, okay, this one here is connected, but let's consider that too. So it's going to be 1, 2, 3, 4, 5, 6 nodal locations. Each of the nodal locations, if I model this by using the simplest possible planar beam element, consists of 2 degrees of freedom. So each of them have 2 degrees of freedom. So in total I have 12 degrees of freedom. So it means that this kind of finite element, which is modeled by using, again, the way I just mentioned earlier, like this, have 12 different ways that the structure can deform. 12. What are these different ways? Well, of course, the way that will be very important for us will be something that it deforms like this. That's definitely going to be something important, and that could be considered as a deformation way ID number 1. But then there's going to be also the deformations where the deformation look like this. because it's possible. It is very real possible. And what do you think when you have a loading case like this, or when you have a deformation like this? Is it something that you really need to know? No, you really don't need to know that. But it's still a part of your equation of motion. It is part of this equation here. So what I do in my modal reduction technique, when I'm moving from nodal space to the modal space, is that I started to ignore some of the ways structure can deform. I could just do the way that I can assume that probably the one way that the structure can deform is going to be like this. This is, now I need to emphasize that this is a way structure can deform. You can express this way structure can deform by telling what is a relative, and now I need to emphasize what is a relative displacement between the nodal decrease of freedom. So they can move the way that this behavior is going to be roughly like this. How much is going to be moving this particular way? Is it going to be the one that I saw here, or is it going to be even an opposite direction, or is it going to be more like a significant deformation? This is something you don't know. You just don't know that. But that's fine, because this is the one that is called modal coordinate. So you have the way structure can deform multiplied by possible amplification of that particular way structure can deform. And now this is something important, because I can use as one simple vector here. This could be a scalar component, one single component, and I can get an approximation about one particular way structure can deform. Now if I'm very lucky, this particular way that I'm just describing here is enough to get the correct solution. Maybe I'm not enough lucky to get this exactly correct answer, but I can get another way the structure can deform. Let's call it as a deformation mode number 2. Deformation way number 2. And the deformation way number 2 could be, I'm going to change the color. Let's put it back. So it could be like something like this. And again, I'm just telling the way the nodes are moving with respect to each other. Nothing else but the way. How much this is needed, I don't know, but I'm going to call that as a P2. So I can collect these ways and amplifications to one single package. And this allows me to move from nodal space to the modal space, where the unknowns are no longer nodal displacement, nodal decrease of freedom, but modal amplifications. Modal amplifications. All right, this is extremely important. So how well you guys are able to follow me so far? This is like something that makes sense. You can follow me like entirely. No problems at all. So some problems. So should I repeat it myself, or what should I? Would it be okay if I just summarize it one more time? Okay, so let me clear this slide. And now will be a good opportunity to get a coffee coupon. You just say that I don't get it. I think that you're confusing, Aki. So that's going to be definitely worth 2 coffee coupon. All right. So again, here's my 5 elements. And when I'm using my 5 elements, I can get my equation of motion, which we can practice a little bit, like how exactly you can get these equations of motion. We can practice that next week. So the dynamics of the structure look like this. This one here is this force that is imposing here. So it's imposing one single nodal decrease of freedom. So it's quite easy to understand. This is a stiffness matrix. This is a displacement associated to each of the 12 nodal degrees of freedom. Where this 12 is coming from the fact that I have here a total of 1, 2, 3, 4, 5, 6 nodal locations. Each of the nodal locations have a 2 degrees of freedom. So that's going to be a total of 12. So this vector here consists of 12 components displacement 1, which is considering this node here in this direction and rotations, which are, you know, constrained to the global coordinate, so it's not moving anywhere at all. But then the next one is going to be this one here, like how this one was like this. Second one was a displacement in a node 2 in a transverse direction, and so on and so forth. So this one here consists of a total of 12 components. These 12 components tells you that, okay, structure have 12 different ways it can deform. 12 different ways. Maybe I don't need to know that many. Maybe I'm happy with a little less the way that the structure can deform. So what I can do is that I can look at this structure as an entire structure, no longer as a one single element, but entire structure. And I can make assumed deformations. Probably the assumed deformation could be like this. This is the way structure can deform. I don't know how much it can deform in this way. It's like one possibility, but how much? I don't know. So I'm calling this way as a vector, like this, vector 1. I don't know what the heck this vector is called, like C, whatever, that doesn't matter right now. So it's just that you know it better than I do. Then how much this particular way, this is going to be P1. So it's a multiplication or amplification of this particular way. This is how I can get approximation for each of the nodal displacement. But there's only one way. Maybe I need another way. Maybe I need a third way. Maybe sometimes I need each of these 12 different ways. Maybe that's the case. But typically I don't. Typically I can survive much less than that. Now, this is what allows us to move from nodal space to the modal space. When we do that, we have something that relates these two spaces, and these two spaces are related because we know the way structure can deform. Okay, only remaining question is this. How we know what are the ways structure can deform? Is there any way to know that? Yeah, there is actually a way to know that. What we can do is that we can look at the vibration properties of the structure. We can compute something that is called eigenvalues and eigenvectors. You know, eigenvalues is a natural frequency of the structure. So what are the components? What are the information we need to know to get the eigenvalue of the structure? We need to know stiffness and mass. These are the two components. Nothing but these two components. All right. Sorry guys that this comes with a little bit of delay. But if I look at my equation here, I have here, so it's supposed to appear to you momentarily, I have here a component that is associated to mass, which is mass multiplied by acceleration. Then I have here a component that is associated to stiffness, which is my stiffness matrix. And then I have one more component that is external applied forces. So when I look at the vibrational properties, first thing that I do is that I don't care about the external applied forces anymore. I just don't care about that. I'm saying that force is no longer considered. It's going to be equal to 0. Equal to 0 means that I'm just looking at the structural properties by using combination of inertia and stiffness, mass and stiffness, mass and stiffness. That's basically what I'm looking at. Nothing else than that. Nothing else than that. Because if you have like, where should I put it? Here maybe the good way to put it in a drawing. This is something that they teach in a bachelor level, I believe. So this is a mass and a spring combination. Mass and a spring combination. And you can compute the eigenvalue, eigenfrequency. Like what is the frequency? This is there's this critical frequency. You can compute it by using a square root of mass divided by stiffness. Here is a stiffness here. So if there is a, let me see if this goes correctly. Yeah, this goes correctly. This is how you compute it. This is exactly what we do for the finite element modeling too. But we're gonna get, is it the other way around?
I think it's the
Other way around, that's what I was thinking too. So it's, let me correct it, so it's omega, stiffness, mass. Let me think. Because if you have a high mass and low stiffness, then your frequency is gonna be very low. Correct, and then this is the way it behaves. If you have a high stiffness, a low mass, your frequency is gonna be high. Yeah, exactly. This is how it behaves. So, sorry, so it was stiffness divided by mass. Because if your spring coefficient is extremely high, you have very little masses top of that, your frequency is gonna be sky high. Now, this was a 1 degrees of freedom system. And our system here, this cantilever structure is a 12 degrees of freedom system. But again, we can solve the eigenvalues, which is going to be a total of 12 different eigenvalues, and corresponding eigenvectors, which is going to be again 12 of them, which gives us all the features of the structure. And then we're going to handpick some of them, making use of some of them, and ignoring the rest of them. That's what we're going to do. All right, so we need to conduct an eigenvalue analysis to get what we call as a way the structure can deform. It comes out of, there are other ways that we can get it too, but the most commonly used are the ones that are based on eigenvalue analysis. So basically, it goes like this. This is your equation of motion when the force is assumed to be 0. So no forces. Here comes the first very important lesson, because what you can get as a result of your eigenvalue analysis is you're going to get eigenvalues, which is corresponding to the natural frequencies of the structure. Now, if you have a 12 degrees of freedom in your system, you're going to get 12 eigenfrequencies. These are the critical frequencies that the structure started to go crazy if you impose those, but that particular frequency. And it goes crazy in 12 different ways, numerically. In reality, it goes crazy in infinite number of ways. But some of the ways that can go crazy are so high frequencies that are hard to excite those high frequencies that they really don't matter. Usually the low frequencies matters, and it works like this. If you have a mass in the spring, and then you introduce the force that is a function of time, when you hit the same frequency, the structural natural frequency, the amplitude, this x started to go really, really high. In theory, it goes infinity. In reality, it cannot go to infinity because there are, of course, something that comes into play and stop it vibrate like crazy. But it behaves like, if this is a time, this is an x, it started to go like this. It really started to go like, this is an exponential curve that is started to vibrate, really like crazy. Okay, that's what the natural frequency, eigenvalue, is standing for. Eigenvector is a way this deformation takes place. A way deformation takes place. And now very often I heard the misunderstanding that when you get an eigenvector, you can define the displacement based on the eigenvector. You cannot. You cannot. It is just the way structure can deform. And you cannot simply because you got it by assuming force to be equal to 0. So it's not about actual responses. It is about the structural behavior. Structural behavior, not actual absolute responses. You just don't know what are the responses. You can get it later, but you cannot get it directly from the eigenvectors. An eigenvector, one more time, is a way structure can deform. All right. So here's my equation of motion. So what I do is that I'm setting force to be equal to 0. That's the first step. Second step is that I do know from the mathematics that there's a correct solution available, and the correct solution is as follows. There's a vector. I don't know what the heck this vector is called. Psi. Let's call it this psi. It may be psi or maybe something else. What is it actually? phi. This is phi. All right, so there's a vector phi, and then there is a e power I omega time. And once you substitute that information to your original equation, you can express it as this. So you get two components. You get here mass minus omega power 2 multiplied by mass. This is your first component, and then the one that is left is going to be this remaining vector. Now what you do for this solution is that you will take this component in the left side. You are look at what are the ways this left side component becomes to be 0. And of course the bulk, let's say, ugly way to look at this thing is that you simply take these components in the left side, you compute the determinant out of it, and then you're solving omegas out of that. And then once you get the omegas, then one omega at the time you substitute it here, and then you get this eigenvector. So this is the way structure vibrates in that particular natural frequency. Okay, clear, becomes to be clear. Again, so we got this value, which is a natural frequency. This is when the structure goes crazy. It started to, the amplitude, the vibration amplitude started to increase exponentially. And the way it goes exponentially vibrating, that's going to be told by eigenvector. Eigenvector is a way, eigenvalue is what frequency that way happens. If the system is excited in that particular way. All right, now something that I need to emphasize here, and then we're going to revisit in Socrative. Okay, again, so if you have a structure that consists of 12 degrees of freedom, this one here. Oh, big mess here. Let me clean this. Okay, not willing to clean it anymore. But again, there's a 12 degrees of freedom in a cantilever beam. If you conduct an eigenvalue analysis, you can get these 12 different eigenvectors and eigenvalues. 12 different natural frequencies, 12 different ways it can vibrate. In reality, this already discretized structure, in reality there's an infinite number of eigenvalues and eigenvectors. But some of them are such a high frequency that is, they really don't carry any practical meaning anymore. So they are just, you can simply, there are not even ways to analyze those in reality. You can analyze these frequencies and the ways by using something that is called experimental modal analysis device. It is, I don't know if you have ever heard about a device, but it's a device that is, there's many different ways. It basically relates to input and output. Input will be something that you excite your system by hammer, or something that is introducing the, a little bit of excitation to the system. And then you're measuring the responses using accelerometers. Sometimes you're measuring the responses using laser scanning. There's many different possibilities. But this is a device that tells you automatically structural behavior. So you don't need to necessarily compute those by using finite element modeling. You can just measure them too, using this experimental model analysis device. We do have here in LUT, we do have this kind of device, and I'm pretty sure you will make a use of that device. You can excite your structure by using hammer, which is like an impact that will make many frequencies to vibrate, and then you just look at these vibrations by using accelerometers or laser scanners, or you could just make your system to run. You monitor the behavior by using laser scanners. So there's many opportunities. But you haven't used this device yet. You have it already. A little bit. So you know how that physically look like. And you can get, there is a many extension of that experimental model analysis device. You can even find even the noise sources. You can see, okay, what exactly is the one that keeps this noise, and you can use that in a spy technologies as well. So you can monitor the window, and this window is vibrating because of my voice, and it can even take that in. I don't know if you can use that in that. I think that you can use it in that purposes too. Is it really that sensitive? What do you guys say? Like if I'm speaking here and somebody is scanning that window, can they hear what we are speaking here? Maybe. We need to ask this from Jussi Sopanen because he knows it. But it's extremely sensitive device. If you walk in a concrete floor, it can hear it definitely can tell how much you're introducing the vibration to the building. It's amazingly sensitive device. But now I got confused. What was my story here? Yeah, I wanted to say that, if there is a 12 degrees of freedom, not a degrees of freedom, that's going to be the number of unknowns in your model analysis. Okay, and now I'm ready to move on to my in-class quiz. Now the final term model here consists of m number of elements and degrees of freedom. It was pretty much similar that we look at this cantilever structure. It was consisting of 5 elements, 5 nodal locations, and it was 6 nodal locations, 12 and nodal degrees of freedom. The model can be used to solve how many number of eigenvalues in theory. And it's going to be either the number of elements, number of nodal degrees of freedom, number of elements minus nodal degrees of freedom, number of elements added by nodal degrees of freedom. One rule is correct, and now I need to move back to the Socrative to see how we're doing there. Okay. You guys don't see there's a major delay, but I'm going to tell you that we got the 41 answers in first in class quiz, which is a physical interpretation of shape functions. And the success rate, 93, which is fantastic. It do not define the strain displacement relationship. That's going to be kinematic matrix doing that for us. No clear interpretation. Okay, so interpretation is a little complicated. So one that is avoiding that can get the points too. Okay, the next one. Final term model depicted below consists of m number of elements and n degrees of freedom. Model can be used to solve how many different eigenvalues. And these are the options, and now they are matched with the options that are available in my slide here. So what do you guys say? Right, so the concept of resonance frequencies, I'm sure is clear for you. So it basically means that, pretty much what I just explained. So if you have a system that can vibrate, when you hit the natural frequency, the vibration becomes to be very large. And of course, in theory, it goes to infinity. In reality, it doesn't, because there is always a certain number of damping in the system involved. There may be other limiting factors, but basically, when you hit the natural frequency, system started to vibrate like crazy. And you've been seeing these examples all over. Sometimes, you see these affordable car suspension system and you see that the vibration goes crazy. So it's really hit the natural frequency and it goes crazy, particularly if the damper is broken. I'm sure you have seen those cases. I don't know what about this student guild team that went to did this long trip and you were using this 400 euros car. Was the suspension okay, or damper was okay, or not so great? Not that great, I believe. Yeah, okay. But anyway, so we will take a look at the only few videos to make sure that we fully understand what is this concept about. Okay, so I'm not willing to show the videos today. I'm gonna send this link to you so you can take a look at this. Watch video in the YouTube. I want to put this voice to be as low as possible. Basically, there is a system that consists of different It's like 1 degrees of freedom system, 3 of them, each of them having a slightly different natural frequency, resonance frequency. And when you're moving the platform, and sooner or later you hit the frequencies of each one of them. And what the response look like, it's just simply they go crazy. And this is a motion that is in this like transverse direction. And right now is a really low motion, but soon it becomes to be frequencies all the time increased. First, you're gonna hit the natural frequency of the structures that is located in the right side of the platform. Okay? So look at the structure in the right side of the platform. It started to have some issues. It started to introduce the amplitude quite a bit when we're hitting the natural frequency. Also, the second one is moving quite a bit. And I think now it becomes to be clear that the one in the right side is suffering quite a bit. The amplitude is increasing. And in theory, it goes infinity. Of course, it cannot, because otherwise the system will be completely break. But this is what the natural frequency look like. Okay, so it's a 4 hertz. You see that it's pretty wild. When you're increasing, it damps down. So it's okay if you're passing the natural frequency, if you go beyond the natural frequency, which sometimes is the case, particularly in rotating structures. You have a low natural frequency, you want to go above it. And if you are not exactly in the frequency, your operation is okay. If exactly in the frequency, your operation is absolutely chaotic, like you see here. And then the second one is hitting again the same problem. And the other animation that I wanted you to be aware of is the one that is, where is my keynote here? This one. So basically, it's showing you structure that consists of different number of degrees of freedom. So it's getting started. I'm going to put this a little bit bigger first. So first it's going to be showing you the system that is 1 degree of freedom. So then you can see one natural frequency. The one-way structure can deform. And it's pretty obvious. So if it is a beam-like structure, it is like this kind of banana mode that you can figure out. So this is the way the structure can deform. Then you have 2 masses. You can get to 2 separate frequencies. 3 masses, 3 separate frequencies, so on and so forth. So this is the basics. And I would like you to be fully understanding this concept. I know that it's seemingly simple, but sometimes people get confused about frequencies, eigenvalues, and eigenvectors, eigenvalues, and so on and so forth. These are the 2 different ways. Now this is the max number of different ways. If you have 3 masses, it's going to be 3 maximum ways. Now what I'm trying to say here is that some of the ways we don't really care. We just simply don't care. It's the same kind of discretization problem, same kind of discretization concept that is being used. I need to put this keynote back in operation. Same kind of a concept that is being used in a discretization of finite element modeling. Because in finite element modeling, what we do is that we are breaking our structure to a certain number of pieces. How many of them? That's a little bit engineering knowledge. So there's no clear answer to say for each of the problems, like how many exactly you need. But you're discretizing your continuous system to a certain number of points that you are focusing on. And in this case, when it is a cantilever beam, you have 1, 2, 3, 4, 5 moving nodes. Then there's one more node here that is constrained. So it's a 6 nodes, 12 degrees of freedom. This is the first discretization you're using. Second discretization you can use is that some of the way structure can still perform is something that you don't care. You just simply don't care. All right, so, all right, here are the few examples about different kind of let me see if these are willing to. Why is that the video is not doing so well today? Okay. You can play this now. No. Oh, it is playing. It is playing. Sorry. You guys, because it doesn't play here in my iPad, but it plays in your screen. Okay. what I wanted to show you here is that there is two different kind of structures. The one that is a paper roll that is used in a paper making process. This is something that is called tube roll. So it's not having any special features whatsoever. This is one of those dumb rolls. So it's just a roll. But what we do here is that we are conducting an eigenvalue analysis. You see that what are the ways that a structure can deform and associated frequencies. And then another example you see is a hydraulic cylinder. Hydraulic cylinder where the cylinder rod is considered as something we are interested in. So we're conducting eigenvalue analysis for a cylinder rod. And what are the deformation modes and associated frequencies? My story here is that you see that there's many different kinds of the deformation modes. Some of them becomes to be easily very exotic, something that doesn't need to have much of an engineering sense to say that they really don't contribute anything at all. Because we're kind of adding up these contributions, and some of the contributions becomes to be insignificant. And when they becomes to be insignificant, you can say that, hey, your contribution is so little that I don't care about you, go away. This is like, how can I say, this is like a work environment, the most severe working environment ever, because each of the modes have to contribute, and if not, they have to go home. We're gonna ignore them. So we're gonna, what is it they say now? There's some of these reality shows, you're fired. We're gonna fire them, so we are gonna let them go easily. So if they don't contribute, we're gonna let them go. Okay, example about how things becomes to be really exotic. Okay, these are the deformation modes you see that are, each of them are like something that you expect to see in real life. Particularly if you have a loading in the free end of the structure, it is easy to see the deformation, something similar than this. And if you look at the frequencies are like 51 hertz, 148, 47 hertz, 109 hertz. So fairly low frequencies and fairly reasonable looking deformation mode. But if you go higher and higher, soon you're gonna get the deformation mode that are looking like this. Where is it? Like this. Here in the upper right corner, there's a deformation mode which is associated to frequency that is close to 12,000 hertz. 12,000 hertz. That's extremely high frequency. And if you think about the overall performance of the structure, what do you guys think? Can you live without knowing how is almost like this joint axis, how that is expanding? Doesn't make any difference whatsoever. How is that you can even excite the deformation mode like that? You just cannot. It's practically impossible to do that. So you can ignore it, forget about it. So it's contributing very little to the overall performance, so we can simply ignore it. When we do that, then we can reduce the number of degrees of freedom in our original finite element model. Here comes the way it happens. And I see already that there's a typing mistake that was here last year too. But I'm going to explain this to you, and then we're going to take a look at the in-class quizzes. How many wonders we have in this planet? Was it like 7 wonders of the planet? Okay. When I was in your position as a master level student, my professor at the time said that this is 8th wonder of the world. This is a miracle that happens next. Because what we do when we're reducing the model size is going to be very surprising. So we just created this relation between the nodes and modes. And it was, okay, let me try to make this as a best possible drawing quality. It was like, this was the way we did this whole story. N. Okay, so we have the entire behavior, which is described by nodal degrees of freedom, that is then break down to the actual global structural behavior global structural behavior was described by deformation modes and corresponding amplifications. Deformation mode, this is supposed to be 2, and corresponding deformations. And then this is the last one we're taking into account. And then when summing up each of these notation, we can create the relation like this. Now, this is a matrix that consists of each of these vectors. So if you look at this matrix here, it is having columns that are corresponding to deformation modes. This was the last one. And then this one here is how many modes we have in the system. Typically much less than our original nodal degrees of freedom. Now when we're moving from this nodal space to the modal space, happens the following. We can simply substitute this information here. We get this. This was a dot dot because of the linear relation. And F. And we still need to multiply this one more time with the transpose of the modes because this guy here is still expressed in terms of nodal degrees of freedom. Yeah, of course, this have to be expressed by modal degrees of freedom. When I do that, this is what I'm going to get. So this is my ways of structure can deform as a transpose operation, the ways structure can deform, then amplifications. Of course, here the one that is missing is this one here, and this is entire system look like. The beauty, when you get these deformation modes using eigenvalue analysis, that these deformation modes, these ones are actually orthogonal. And now this time they are really orthogonal. So what you can get as a result of that, you get a reduced size of the structure, but the reduced size have another very special feature, which is the fact that whatever is left is going to be diagonal representation. You kind of deleting the relations between the different modes. And that's something that is computationally very positive feature because it simplifies the computing quite a bit. All right, so here's the thing. So I have my next meeting that is getting started at 12:30, and I need to have a lunch before that. So I'm gonna close here, and hopefully next week I will come here well before the lecture because every single Monday morning experiencing these technical difficulties, and I need to make a promise that next week is not gonna happen. So please come over. I will make sure that these projections are cooperating, and the streaming is gonna be with the highest possible quality. But I'm gonna close here today, and before we go, so let me take a look at our results here. Okay, 37 answers, and the correct answer is, of course, B. Very good. So we got 92% is success rate, which is fantastic. Good thing. All right, with this, I'm gonna close streaming.